we'll be looking at properties of the parabola, where the parabola is given, or the function of the parabola is given in the form y is equal to a brackets x plus p all squared plus q. We want to sketch, for instance, the graph of f of x here and g of x on the same set of axes. It will help us a lot to kind of do or carry out some experiments where we draw these graphs. Maybe use a math software to draw these graphs and then compare the two functions. I'm going to draw these graphs together on the same set of axes, and I want you to compare the two graphs and try and come up with your conclusions regarding the shape of the graphs, the domain of the graphs, the range, the turning point, as well as the axis of symmetry. So first of all, I want to draw the graph of f of x is equal to x squared. Right, so y is equal to x squared. I will draw the other graph, which is y is equal to, in brackets, x minus 2 all squared. So the first graph that we got is that black one there, and that is the graph of y equals x squared. But then the next graph, g, is given by y is equal to the square of x minus 2. I need us to take note that there is x minus 2. Right, the format is the same. So what do you realize regarding the shape? You will notice that the shapes are the same. The orientation for these two graphs is just the same. What about the domain? The domain will be the values of x that we can use to get these graphs. And in this case, the domain for the first graph, the black one there, is the same as the domain of the other graph. So the domain will be x element of all the real numbers. Then the range, you will notice that both your graphs have a turning point on the x-axis. So the turning point for each one of them is actually sitting on the x-axis. And so for the first one, the minimum value of that function is given by y equal to 0. So y is equal to 0. The second one, the minimum value for the blue one is also y is equal to 0. All right. And so these two graphs have the same domain as well as the same range. So the range of the first graph and the second graph is given by y is greater than or equal to 0. The turning point of the first graph has coordinates at 0, 0, and the second graph has a turning point at 2, 0. For the first one, the axis of symmetry will be the y-axis, but for the second one, the axis of symmetry will be the line that passes through that point 2, 0 there. It's a vertical line passing through point B, and that line will be x is equal to 2. So we said the shapes are the same, the domains are the same, the ranges are the same, the turning points are different. So I want us to ask ourselves why the turning points are different. And obviously, if the turning points are different, we expect the axis of symmetry to be different as well. So the turning point for the first graph is at 0, 0, but the turning point for the second graph is at 2, 0. The reason why this is so is because it looks like the graph, this black graph here, was shifted 2 units to the right. The funny part is that this is given as x minus 2. Whenever it's a minus 2, you expect your graph to shift to the right. This time, Our graph of f is x plus 2 all squared minus 3. The minus 3 is the same as that q value there. So in this case, we know that q is equal to minus 3. So we're going to draw that and then determine the turning point, the range, and the equation of the axis of symmetry. That is the graph that we get. Look at the turning point. The turning point is down there. The coordinates of the turning point, you will notice, are -2 and -3. And then the range will be given by the values of y. Now the minimum value of y in this case is -3. So that is the smallest value of y, which means our range can be written as y greater than or equal to -3. Our axis of symmetry will be that line x is equal to -2. If you look at that function there, the graph, you will notice that it has a turning point on the left side of the y-axis and not on the y-axis. So you can imagine that the mother graph or the parent graph was shifted 1 unit to the left. But for us to shift 1 unit to the left, it means in there, everything should be a plus. And that means we need x plus 1 inside that bracket. That is what we discovered in the previous examples. So you know straight away from this that p is equal to 1. And then for q represents a vertical shift. Remember that the parent graph always makes its turning point along, or rather at that point 0, 0. And so that graph was shifted 1 unit to the left, and then it was pushed 1 unit up. That is what it looks like happened there. Therefore, we can conclude that q is equal to 1. So you can tell some of these values straight from the graph without working them out. Now we know p and q. The only challenge now is a. Let's put in those values into the equation. We have y is equal to a into x plus p, but p is 1, plus q, but q is 1. So that is what we have. We need to find the equation, which means we need to also know the value of a. And that is the reason why we are given that our graph passes through the point -39. If we take that and substitute in here, we should get the value of a. So where there is x, we put -3, and where there is y, we put 9. This means 9 is equal to a brackets, x is -3 plus 1. So I left the square there. All that should be squared plus 1. Right, now let's solve that and find a. That should give us 4a plus 1 if you simplify that. Therefore, a will be equal to 2. So we now know a is equal to 2, which means the equation that we are looking for is given by y is equal to 2 brackets x plus 1, all that thing squared, plus q, which means plus 1.